Welcome, students, to our last lecture. We have to add our third topic under the heading of statistical inference this morning. First one was estimation, where we're trying to forecast and predict. We go out and take samples of market research from our various market segments, and then we want to forecast what's happening there. Very common. We encountered things in business, so pretty good chance you'll need this some point along your way in business. Hypothesis testing, not so much. You're either going to use this a lot, depending on the industry you're in, or you're not going to use this much at all. The only times I've ever used it in industry is when I've been an expert witness. In a couple of cases, Sunkist hired me to prove that there was a fire aboard a ship, a bunch of oranges, if they didn't get the right price for them. And it was another one. I was in a software piracy case. I proved that the one party had pilfered the software of the other. So, but if you're in an industry where you got government testing and things like that, then you'll be using this. But as a general rule, most businesses don't use a lot of hypothesis testing. But it is still an interesting topic to cover. All right, and then our last topic, which is a very easy one, because all we're going to do is interpret the Excel output and let Excel do all of the heavy lifting for us. That'll be a good way to end things. In hypothesis testing, we have this unknown population. We draw a sample from it. And now we want to generalize, to infer something about the population. Our definition of infer for hypothesis testing is what can you prove or conclude? What can you conclude about the population? In our case study, we're asked to conclude or prove that Otto's going to make a profit by using some handheld computers. All right, so we saw that a hypothesis testing is a courtroom proceedings, and who starts by somebody filing a case, and that is the alternative hypothesis, files the case, what they're trying to prove. And all hypothesis says, no, that's not right, it's the opposite of that, it's everything else but that. Okay, burden of proof is on the plaintiff, and the defendant gets the benefit of the doubt. We accept a certain amount of error or uncertainty. That's called the level of significance. And then we go to court. But unlike our screwed up court systems, we only allow one type of evidence, and that's sample data. What did the sample say? And then based upon that, we will make our conclusions. Okay, I gave you the process here. We start. Read the problem, send out your notation just like we did for estimation. Then you say, who's got the burden of truth? What are we trying to prove? Here's the key. We must state that in terms of a mu or a p. We must state it in terms of a mu or a p. Whatever's left is HO, so we back into HO. It's by default. Okay? Anything that wasn't in HA is HO. The level of significance will be given in the problem. Typically, it's 0.05 or 0.01. We want to be 95% sure you're guilty, or maybe 1% or 99% sure you're guilty. We go to the fabulous handout provided by our wonderful prof on pages 30 and 31, and just follow the rules there. It all comes down to we look at a z-value, which is the most number of standard deviations that can reasonably happen. And then we compare their claim to our result and say, how many standard deviations is that away? If it's too extreme, we reject. If it's not too extreme, we accept. I should have put number 9 in there again. Sometimes you do a p-value, so I'll show you how to do that. All right, so Our first little practice problem was on page 34, number 11. A TV network claims 40% of the viewing public are watching the competitive cooking show where contestants prepare dishes from Southeast Asia. And the series is called Who's the Baddest Pho Cooker in Town? Yes, I wrote that. You will not find that anyplace else. A random sample of 600 families showed that 180 families were watching the show. Yeah, that's pretty good, but it turns out to be that's 30%, but they're claiming 40%. Why would we be concerned about this? Well, maybe we're thinking of advertising some food product on this show, and the amount we pay for that ad is directly proportional to the ratings of the show, how many people are watching. So we think we ought to get a reduced rate because we think they've overstated it. Can you show it's not as large as they claim at the 0.05 level of significance? So we want to be 95% sure they're wrong. So here we go. What do we know? We don't know anything about the population. It's certainly qualitative data. Hello, calling from baddest pho cooker in town. Are you watching this show? No. Okay, you ought to watch it sometime. Yes, thank you for watching. Yeses and nos, qualitative data. So I got 180 out of 600, so we think 30% of the people are watching out of the 600 we sampled. What am I trying to prove? I'm trying to prove that the proportion of all of the viewers, P is the proportion of all of the viewers watching this show is below 40. And they claim it is 60, 40 or more. 40 or more. Whatever is left, whatever isn't covered in the alternative is what the null is. So we go to our fabulous, I forgot our fabulous handout, and we say, okay, was it quantitative data or was it qualitative data? It was qualitative data. Did we take one sample? Yes, we took one sample of 600, so it's greater than that. And are we trying to show a not equal to? We don't find not equal to's very often, especially for qualitative data. Once in a while, we find a not equal on quantitative data. Like we say, I want, produce me a batch of nails 2 inches long. Okay, if they're a little low, it's a problem. If they're a little long, it's a problem. In that case, either low or high is bad. But usually it's only bad if it's either low or high and not both. Our case, we're trying to show something's less than something than they claim. Yeah.
Will you knock us off if we do the equal to or not?
Yes, I will. Question was if.
In the problem, it says the network claims that it's 40%.
Yeah.
That at least 40%.
Yeah, but look at the economics of the problem. Look at the reality of the problem. Okay, if we find out that 60% of the people are watching the show, are we going to go to them and bitch? Are we going to quietly pay the ad and know we got a deal? We're going to pay for the ad and know we got away cheap, and we're not going to tell anybody about the fact that their viewership is much larger than they made a mistake. So economically, or in a reasonable fashion, it's only the lowercase that's a problem. If people in their ads understate the product, nobody's got a problem with that. Understate the viewership, nobody's got a problem with that. So these are very rare when we do a not equal to. It's got to be low's bad, high's bad. Both are bad. Both are proofs against our statement. All right, so here's our case study. Here's our setup. Here's what we're going to do. We're going to compare this table value for Z against the number of standard deviations that we will that's our toleration, and this is what we saw in terms of standard deviations. Okay, so we just go look up the Z 0.05 value table, and then we plug into here and figure out how many standard deviations our observation is away from their claim. So we look up one of our old reliables, 0.05, and we find that that is equal to either minus 1.64 or minus 1.65 steps away from center. We plug in our values, and you are to rewrite these values. Some people on the exam just write that formula there and don't plug in the values. Okay, I'm going to mark you off for that. You know, yeah, so far so good, but you didn't finish. You got to finish. You got to hit the ribbon before you get credit for it. So plug in your numbers, and yes, I'll give you the check figure. I'll give you the check figure to minimize your calculations. All right, so we got -5 standard deviations. Well, I know already that we've proved our case overwhelmingly. So that is -5 below minus 1.65, absolutely and completely, and we reject HO emphatically, and rejecting HO with an emphatic exclamation point. Okay, any questions on that? Goody, goody. Next, we got L.K. Traz as prison warden at Sing Sing Prison. Been asked to evaluate the effectiveness of a new education program to reduce the rate of recidivism. That's a great word. I took a sample of 200 inmates who completed this course. 80 of them went back to prison within 2 years. Took a sample of 200 inmates and traced them over the next 2 years, and 100 of them went back to prison. So what do I know? What question was asked of each of the inmates? You know, we checked their records. Did they go back to prison within 2 years? And we get back yeses and nos, and yeses and nos. It's qualitative data. We don't know anything about the populations, about who's taken the class and what their rate is. That's why we took the sample to find out. Took a sample of 200, 80 out of 200 are 40%. 40% is the recidivism rate among the people taking this class. Same situation for the control group or the others. The rate of recidivism there is 50%, 0.50. What do we want to prove? We want to go before the state budget committee and say, scientific testing proves that this program is effective in reducing the rate of recidivism with, how certain do we want to be? With 99% certainty, our alpha is 0.01. So we want to go before the state budget committee and make that claim. Sounds good. To do that, we're probably going to get funded. What are we trying to show? We're trying to show that the proportion of the people who are going to get the class, or that was in what I'm calling the test group here, that's why I call it test, the one who got the stimulus, who got the class, is less than the control group. Okay, this is how classic research is done in statistics, where you have a test group and a control group, or an experimental group and a control group. Yes, sir.
I missed where we got the level of this.
It should have been given in the problem somewhere. I couldn't find it. Was it in the, well, I used 1% here. I'd check on that. Do you have, is it in the original problem? When I did the cut and paste on this problem here, then I didn't do the whole thing. Is that what happened? I don't think I cut and pasted the whole problem, or it's in the problem eventually in the workbook, but I didn't put it here. Okay, I should have had it in this point. At this point here also, this thing should stand by itself. So so it's a black mark against me. All right, so okay, so I'm trying to show that the proportion of the people who went back to prison in the test group is less than that control group. The hypothesis is whatever's left. All right, so you've done the hard part. Yeah.
Concerning alpha, the error.
Yeah.
In some situations, there's, I guess, when do we divide by two? Like, I know there's some, do we just follow along with each case?
You, as I said in my instructions, follow orders. Don't think on your own. Do exactly what you're told, okay? Now, when we go to figure out which case it is, okay, we find out it's hypothesis test. It is about qualitative data, but it is about 2 samples. So we're over here in number 4. Both were greater than 30. If we had chose the not equal, then you are going to be dividing by 2, okay? So then, you know, if you picked your case as 4A1, then you're going to be taking your error factor and dividing by 2, okay? If we think it's the 4A2, we're going to do just what it says here. We're just going to plug the alpha, okay? On confidence intervals, you always split the error in 2, automatic. Percentiles, no. On hypothesis test, let the instructions tell you what to do. Just follow the instructions. So our setups here, going to do a Z.01 and find out how many standard deviations that is. And then we're going to say, what's my Z test? How many standard deviations are the 2 groups apart? And see if we can prove our case, if it's more extreme than needed. So we plug in the 0.01 and we get minus 2.33 standard deviations. We, given that nasty looking formula there, plug in our numbers, and once again, our dear and beloved prof has come to the rescue and given us a check figure. Okay. Not everybody does that, as you'll find out. All right, so I get minus 2.02. Is that more extreme than minus 2.33? The answer is no, it isn't. So you cannot prove with 99% certainty that this program reduces the rate of recidivism. But we think this thing really works. What's the problem? The problem is we got qualitative data. A sample of 200 from qualitative data is not very accurate. Okay, you need much larger samples of qualitative data. What do we need? You need to jack that up to at least 400 and you'll be able to prove your case conclusively. But we can go before the board and say what is the probability, what's our certainty level that this is an effective program. That's the job for the p-value. So the p-value, you go back to say, what test did I run here? Instead of alpha, you write p-value, and then you set this equal to whatever value we got for our z test. So we set z p-value equal to minus 2.02. We go look up minus 2.02 minus 2.02, I think that's it. That's 2.02, get 0.0217. 0.0217. So if I said, find me the 0.0217 percentile, you'd say, oh, it's minus 2.02 steps. So then you set these 2 little subscripts equal to each other, and the p-value is 0.0217. There's a 0.0217 chance that this program is not effective, and so there's a 0.9783 chance it is. So we're pretty close to 99. We don't have to increase the sample size much to get over that hump. Got it? I know, it's Saturday, it's raining, I know. All right. Now we come to page 32, number 3, the infamous J.D. Power problem. It's infamous for several reasons. I'll tell you about a couple stories behind this one. J.D. Power, noted automobile expert, just completed a mileage study about a recently introduced car, following the trends of naming cars after planets like Mercury and Saturn. The manufacturers obviously chose what planet? Uranus. The car is so responsive to the driver that the slogan was chosen to be, "You can feel the road with Uranus." Sorry, I thought that was funny. The mileage per gallon is 5 random select cars was blah, blah, blah. All right. So here's a case where I give you a little bit of data, and then I ask you to do a hypothesis test about it, okay? So I add up each of the things, and I get my sample mean of 35, and I take the differences between all these values and the sample mean and square them and add them up, divide by n minus 1, and I get S squared and S, yes.
On the exam, do we have to go through the variance?
On the
formula first?
exam, you must give me this.
And then can we just do the standard deviation formula?
What do you mean the standard deviation formula?
Like you're doing the variance formula and then doing square root. I just use the standard deviation formula.
Well, we got to do these same calculations regardless, okay? If you just go straight to the square, you got to do this 24 first.
Yeah.
If you just put S equal the square root of 24 over 4, that's fine. Sure. All right. All right. And you will leave it as 24 over 4, and I'll give you a check figure too. So, okay. So you won't have to do a square root. Okay, so we got our data. The manufacturers claim that the car gets 38 miles per gallon. And we did a study and we found that our average was 35. Okay. So obviously this is quantitative data. What do we know about the population? Nothing. Don't know how many cars were made. We don't know the average mileage of every car. We will never know those. Took a sample of 5. Found that the average mileage was 35 of those, and a little variability measured by sample standard deviation of 2.45. We are trying to show that they are guilty of overstating the mileage. And our federal government takes a very dim view of that. Okay? A very dim view of that. The null hypothesis is that, oh yeah, it's 38, or yeah, it could even be more. So we have an argument, and we're going to settle this argument. So I go to my wonderful handout that makes this boring and difficult topic absolutely simple. We have one sample, quantitative data. First case, so our first example where it is less than 30. We only sampled 5, as in 1, 2, 3, 4, 5, one handful. Okay, so it is a 1B, 1B2. What does it say down here? It's the same as 1A, only substitute T, whatever percentile you're asked for, instead of a Z. So you just go to the Z table to get your extreme value instead of the Z table. It is a 1B2. We would run it as this, but I'm going to look up T alpha, not a Z alpha. But I'll use the same Z-test formula. So we head over here and we say, all right, I needed a Z alpha, but then you told me to substitute T alpha, comma n minus 1. So I need to look up, our alpha is 0.05, and then our sample size is 5. 5 minus 1 gives us what's called the degrees of freedom, which is the rho value in our T table. So in the previous problem, we needed 1.645 standard deviations to be extreme. That's going to change here because the T curve is not as precise as the normal curve, so we have more uncertainty. So we head to our T table, looking up in the 0.05 percentile, down to row 4, and we see it's minus 2.132 steps or standard deviations. That's our threshold of being too extreme or not plausible. All right, so we got that, and then we say, okay, how many standard deviations apart were we? 35 minus 38, boom, 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 minus 2.74. And I'm sure the makers of Uranus are going to be shocked. They would say, a sample of 5 can't prove anything, right? I guess they haven't heard about the what? About the correct response is awesome power of sampling is the correct response to that. Awesome power of sampling. So we have proven with a sample of only 5 that they are guilty of false advertising. If we look at the case against Hyundai and Kia, okay, in 2014, they were assessed $300 million for overstating their mileage of their cars. And how did the government prove their case? Anybody want to wager a guess? Hypothesis testing is how they proved their case. Up to this point, it had been the biggest fine ever assessed against an automaker. Of course, Volkswagen later blew that one out with what they pulled, you know, with the programming the things to beat the testing at the smog things, blatantly. But the sad part was Hyundai and Kia had been doing a terrific job, and J.D. Powers had said that they were pretty close to a Lexus on first-year quality and first-year satisfaction of the buyers. So they really didn't need to do it, and they screwed the pooch. You know, much like Toyota was doing so fabulous, and then they had the problem, and then they danced around it, and they just dealt with it poorly, and it hurt them and took them a couple years to get back, you know, where the accelerators were sticking. All right, so yeah, this was used, hypothesis testing was used to prove this particular case. All right, so why is this called the infamous J.D. Power problem? A couple of reasons. Number one is early in the 80s. I started my company, and my 2 or 3 first, I had like 3 clients going at the time. I had the Directors Guild of America going, and I had a small Practical Peripherals, this is my client, going, and I had O'Gara Auto Works. Yeah, O'Gara Auto Works. They were a manufacturer of limousines. And it was a startup company in Simi Valley. And so they asked me to join the board of directors. So I show up for the first meeting, got there early. And I'm sitting across from a Midwestern looking gentleman, very quiet. And I say, hi, Tom Waddell, how you doing? And he say, hi, Dave Power, how are you? J.D. Power, John David Power. He was on the board too. So we got to talking, what do you do? He said, yeah, I got a software company and I'm doing this manufacturing system for him. What do you do? I said, I do automobile surveys. I go, what a boring job. He's doing automobile. I said, how many employees you got? He says, 7. And I said, well, I got 8. So I was bigger than they were at that time. Okay. And he says, what's your background? I said, oh, we got a PhD in statistics. Oh, PhD in statistics and, computers? Maybe, we'd work something together. I'll do something. Because I just got a contract to do buyers. Up to then, he'd just been consulting for automobile makers on what they could do about their product. And now he got the contract to do the buyer's satisfactions for all cars. And anyway, I was too busy. I was working 80 hours a week. I shined him on. And he went on to great fame, of course, and did very well. I begrudge a lot of people their money. I do not begrudge Dave Power any money that he made. He is an honest gentleman. He's just a good guy, a principled man, and deserved everything he got. He lives over in a mountain in Oak Park. I live on a hill in Thousand Oaks, so it's okay. Anyway, that's the first story. Second story is about 20 years ago, I give this problem in my stat class, and one of his employees happens to be in my stat class. And he emailed it to another employee, who emailed it to another employee, and pretty soon everybody at J.D. Power has gotten this problem, this very problem. So the CEO, which was Dave, had moved up to the chairman of the board by then. The CEO found out where it started, calls this student in and says, is this from you? I mean, did you write this? And no, that weird prophet who knows Dave wrote this. and eventually I had a good laugh about it, but he raked him over the coals a little bit before saying, oh, okay, it's funny. But that was okay. That's a true story. All right, so the part B of this problem, the manufacturers of the car claim that here we go. We also conducted a buyer satisfaction study on this car. Asked 400 people. 280 said, yeah. Okay, so can you disprove the manufacturer claim? So we got this sample. Hey, what question was asked 400 times? Are you happy with Uranus? Does Uranus work okay? You're the people with the problem. I'm just saying what the question was in this survey. Okay. So what do we know? I don't know how many cars were sold. I'm never going to know I'm never going to do a census. I grabbed 400, and I try to do a census. I send a bingo card to every purchaser of the car. They don't all respond though. I get a p-hat of 280 out of 400 said they were pleased with the car's performance. Okay, so they say it's 80 though. Okay. So we think it's less than 0.80. And we think they're overstating the popularity of the car. The HO is exact opposite. All right. And we got a case of 3A2. And reject HO if Z test less than Z alpha. Z 0.05 is minus 1.65, one of our usuals. Bingo. Tango, bongo. And got a Z test to minus 5. We crushed it. There, we're absolutely certain they're lying. They overstated there. I don't think the government's case against Kia was this strong. This is extremely strong. 5 standard deviations away. Not in this lifetime. All right, so that's the subject of hypothesis testing. All right, as true with all things, okay, you know, you go to see a rock act or a comedy act, you know, you always close on a high note. You always save your best stuff for last. Regression and correlation. Virtually guarantee you are going to use this in your business career. It's really good stuff. Very practical. Our illustrated problem is page 38, problem 1. Suppose it's 6 years from now and you finally have your MBA. Let's be optimistic, okay? Let's be really optimistic. And let's even go further out on this shaky limb. And suppose you have a job working at this company and a non-relative hired you, okay? That's a further stretch. And this manufacturer is a custom, automobile custom license plate. They got a 2-week backlog, and your boss has come in and said, how much money are we going to need to run the business next week? I want to make sure we got enough money in the bank. I heard you got a B- in SOM 591, so you should know how to do this. All right, so you go out, and what's the first thing you do? You gotta collect some data. You collect some data. You collect some data for the last, I think it's 30 weeks, okay? And we collected data on how much was the cost of production? How much was the cost of production during the last 30 weeks? But I also, smart person that I am, collected some other data. How many units did we produce in each of those 30 weeks? Okay. Up to now, we've done our samples. We've only asked one question. You know, how much mileage did you get? Okay. I only ask one question. Now, what's different about regression is we ask several questions. And we want to know, are the answers to those questions related to each other? Why did I pick the quantity produced as what I asked? Well, there should be a close relationship between the quantity produced and the cost of production. Accounting theory says it. You know, it's fixed cost plus variable cost times quantity produced. And the other thing is, we know what X is going to be. We know what X is going to be. So can I use information about something I know or control to predict better something I don't? Because without this, all we would do is add up these costs and say, oh, our average cost is $9,000 per week. And up to now, that's what we would forecast. Okay, and we got some variability here. So just guessing the average cost per week, you know, it's better than doing nothing. But, you know, if we measure that, that's not too accurate. That's not great. That's pretty, compared to those two, that's a pretty high number. So we want to know, can I do better than regular old sampling and using the sample mean? Well, we call down to the scheduler and say, okay, what do we schedule? What's the scheduled production for next week? And they tell us it's 4,500 units, 4.5. Well, the average production is 3. If they told me it was 3,000 units, then 9,000 would be a good guess. But now they've told me we're going to have a high month of production. So I don't think that 9,000 is going to be very accurate. So accounting theory says there should be a relationship between X and Y. That is a straight line. But then the clincher is this scatter diagram. I've plugged all those points in. And I've done what's called a scatter diagram. I've got my X and my Y plotted together here. And we see that there is looks like a strong linear relationship. It's not perfect. There are points that are off the line, but it's a pretty tight fit all the way through. Okay. What errors do we have? These distances off the lines are our errors. And what regression is going to do in Excel is going to take these little square distances and add them all up and say, find me the line with the smallest squared misses. And that's called the least squares regression line. And that's what's built into Excel. The criteria it uses to find the best line is, out of the infinite number of lines I can put, they go down, they go up, they start here, they start there. Find me the one with the minimum smallest squared misses. These vertical distance squared off of the line. All right, so we do that. I went in and plugged that into Excel regression, and I got the following output. Here's everything, okay? Let me show you what you got to know. Step one, look at the p-value column here. P-value, p-value. I've heard of that somewhere before. We talked about it sometime this semester. I forget. What subject was that? Oh, hypothesis testing 20 minutes ago. Okay, p-value. P-value. If a p-value is real small, what does it mean? It means we've proved something. We want small p-values. Our typical cutoff is a p-value of 0.05. If it's below 0.05, it's good. Because the p-values are errors. So what's the p-value on this? Is first thing here, 0.0018. That's good. What's the p-value here? 5.23 e to the minus 8. What the? Okay, well, I don't know why Excel does that, but see, Excel didn't want to write 0.0000000523. It says move the decimal places 8 places to the left. Okay, this is a much smaller value than the one right above. Very small. All right. So I look to the p-value column. Are all of the p-values below 0.05? Yes. It means this equation is good to go right now. This equation has no dead wood in there. There's no noise factors. There's not some other stuff in there that we don't want. This is all good stuff. Good to go as is. That being true, then we walk next to the coefficient column. And here's my equation. Here's your equation. Get your equation. My equation is intercept. That's the constant. 3 plus 2x. The equation that fits this line. Out of the infinite number of equations I could have put to this line, the one with the smallest squared misses is 3 plus 2x. Right, and then that allows us to make our forecast. So we take this and we make our forecast. My forecasted production, or my forecast of production cost when we're producing 4,500 units is, plug in 3 plus 2 times 4.5. You take the 3 plus 2 times the 4.5, and we get 12,000 bucks. I think we need 12,000 bucks to run the business next week. The 3,000 is our best guess as to the fixed cost per week. The $2 is our best guess as to variable cost per unit. Gee, I wonder what topic is big time on the CPA exam. regression and correlation. The number one ways of estimating fixed and variable costs, because things change over time. All right, so I made my forecast. So you go to your boss, say, boss, I forecast we need $12,000 to run the business next week. And your boss says, okay, great. I'll go make sure we got 12,000 in the bank. So no, I'm 100% sure we got enough. And then you say, oh, sorry, boss, I didn't say 100% sure we have enough. The boss says, how sure are you that we have enough? Oh, 50% sure. 50% sure we got enough, 50% sure we're going to run out. What's going on? Of course, we got a bell-shaped curve. We're setting at 12 is the center point. All right, what do you need to know? So you know everything there is. I gave you the center point. You need to know the shape of the curve, the step size of the curve. I don't want to call it a standard deviation because that has other connotations. Just the step size of the curve or the shape of the curve. And where is that found? That is found right here. It's called the standard error, or the standard error of the estimate. And that is your shape curve, your shape, your step size. That's the step size of the curve. So how's that determined? We take each value and we subtract how far we are away from the line, square them, and divide by n minus 2. Okay, you will never have to do that. All I'm asking you about is the interpretation of the Excel printout. Okay, but that's how Excel did it. All right, now I know that. Okay, boss. Okay, here. After this, I want my review. Okay, I predict we need $12,000 to run the business. I'm 68% sure it's between 1033 and 1367. Oh, I did 90. Plus or minus 1.67. Yeah. And if I walk 2 of those, I'm 95% sure we need between $8,660 and $15,340. Now give me my raise. All right. Last thing you need to know from our little table here. Okay, I put the whole shot in here explaining everything that's really significant in case you ever need this out in the real cold, cruel, real world. Okay, and so if you need it for later use. But in here, so p-value, gotta know that. Gotta know what the coefficients mean. Okay, you gotta know the standard error. If I do a confidence interval, I'll use that. And then the last thing I want you to know is the adjusted R-squared. The adjusted R-squared is a ranking mechanism of how good a estimator we have. And it's on a scale of 0 to 1. 1 is nirvana, perfection. 0 is my brother-in-law. Okay? No, no, 0 value. What does the R-squared represent? I don't know why Excel gives you an R-squared and an R-squared adjusted. I don't know why. And the adjusted R-squared is more accurate. But you take a large sample size, they're virtually the same, as you can see there. So what is the adjusted R-squared? It says out of that the variable cost, once we take into account cost I'm sorry, let me start that over. Let me get it right. I know it's Saturday and wake up. Get it. Once we take into account the number that we produced, okay, and incorporate that in our equation, that explains 65% of the variation in cost. That the equation, which incorporates the number that we produced, okay, explains 65% of the variation in cost. Looking at it another way, 65% of the variation in cost is explained or reduced by the regression line. 65% of the variation in cost is explained or reduced by the regression line. You know, so on a scale of 0 to 1, it's a 0.65. You know, is that great? I don't know. You know, so 65 on an exam good? Well, if it's econ, it's great because they're hard graders. If it's, what's another? If it's 591, oh, it's horrible. Okay, it's an easy class. It's whatever. Okay, it's whatever's out there. We just go with the one that's highest. Okay, you take the highest you can get. When I did my doctoral dissertation, I got my R squared up to close to 50%. And you say, oh, that's no good. Well, the best one so far was in the 40s. And I was trying to estimate the value of offshore oil reserves a couple miles under the seabed using 30-year-ago technology. So it was, better than anybody did before. So, a little better. So, we just, you take the best you got. Okay, if this is the best we got, then, that's the best we can get. We will opt for which, the p-values are going to tell you which ones are the winners. Okay, and then whatever there are squared, that's life. All right, so let's see what else. That's everything you got to know in here. I'm just telling you some neat stuff here. If you're an accountant, you would be interested in, is the fixed cost exactly $3,000? No, it isn't. We have uncertainty about that, right? And what is the step size on that curve? Right there it is. And give me a 95% confidence interval on the fixed cost. Oh, there it is. Okay. It's not exactly what we would get because they, for us to do a 95, we just used 2. They're much more accurate. They did it using a T and not rounding it off like we did. Oh, you think the average cost per unit is $2? You think it's actually that? Yeah. Well, here's your uncertainty regarding it. I'm 95% sure it's between $1.44 and $2.56. So it's giving you a bunch of other stuff that's useful, but for our purposes right now and for the paper, we don't need to go into any further into it. All right, so this standard area, the estimate, sometimes has this little symbol called S sub E. So I should tell you that. What else? Okay, so here's our process. Perform regression in Excel, including all relevant variables. So you throw everything you could possibly think about that might be related to what you're trying to predict. Then you regression churns them all and then gives you the output. Check the p-values. It'll tell you who's the winners and who are the losers, which ones are significant, which ones aren't. Okay. Now, if you find some that are not significant, you need to get rid of those. You don't just drop them from the equation. That don't work. You must do regression again without them as independent variables. The y value is what we're trying to predict, is sometimes called the dependent variable. The x's we're trying to use to predict are called the independent variables. So go back and eliminate any insignificant variables. Okay, and run regression again. Okay, get your equation, make your forecast, use the standard error of the estimate to construct the confidence intervals, interpret the R squared. Tell you how good you are. All righty, we'll do one more example of that. In regression, okay, regression looks at the association between two or more, usually quantitative variables. It finds the equation of the average relationship between variables. Correlation determines the strength or significance of that relationship. The variable you're trying to get, the variable or variables, the independent variables of x's, whose future values are known, okay, that you're hoping is significantly related to the dependent variable, which you're trying to guess. So you pick x's that you know something about or control in order to predict the y. Then we use the forecast and we make our confidence intervals. The x is sometimes called the explanatory or predictor variable, and the y is sometimes called the response variable. What we're doing here is statistical inference. We have a population. It consists of all the x's and y's that would ever be. We grab a sample of it, and we say, what sample, what relationship did we see in the sample? Here's my intercept, here's my slope. Don't let this mathematical jargon knock you down. All right, so if I get a plot like that, that's a perfect linear relationship. We dream about that. R squared would be 1. Your standard error of the estimate would be 0. All points dead nuts on the line, no distance off the line. What we had? We had a good linear relationship. That's a good linear relation. Good straight line fit. We got our SE was 1.67 and our R squared was 0.65. Pretty good in the real world. It's a cruel, uncertain world out there, folks. Here's the X my brother-in-law suggested. Basically a shotgun blast, which means there is no relationship at all between X and Y. In fact, the line that best fits this data, Y bar equal 9. The average, just every point, our best guess is 9 because there's no relationship between the X and the Y's. So R squared would be 0. And the best fit for this line is just guess the average Y because X tells you nothing. And SE is 2.80. Where'd that 2.80 come from? Okay, it comes from the inherent variability in Y. The regular old sample standard deviation for Y is 2.80. That's where that came from. Okay, this variable didn't reduce it at all. It stayed the same. Same uncertainty as before. All righty. All right, here's one we often see, especially today. Getting all kinds of compound growth rates, technology-related stuff right now. Okay, this is a good exponential relationship, and we can use a modified version of regression to do it, okay? And you can look at any number of sources that'll tell you how to do it, but this is a good exponentially relationship to it. So what you do is you take the logarithm of each of the X values, and then you plot that, and that should come out to be a straight line relationship to what it is you're trying to predict. If you have a logarithmic, where things are declining at a given rate, okay, then that's called logarithmic growth. If you have that, you can also adjust for it. For logarithmic growth, you take the X values, take the exponential value of it, and then that will plot a straight line. All right, and you can see there's some things on the internet that'll tell you how to do that. What can we expect 3 days from now? Our final's in 3 days from now. Great. All right, I will give you a problem. Matter of fact, I'll probably give you this exact problem with a few numbers changed, okay? In fact, you'll notice that this is very similar to the one I put out there for the sample final exam that I finally conceded in. You know, if I wanted to be nagged, I'd go home. You know, you're nagging at me. Haven't I done enough? You know about my double hernia already. You're trying to get me into some kind of mental thing too, you know. I give you a printout like this and ask you to do some of the following steps. Part A, okay, if X equal 80, forget the thousands, 80 X period forecast demand, okay? So first off, both are significant. P-values are both below 0.05, so it's good to go. Okay, so here's the equation. What's the equation? 300 plus 5x. Plug in 80, I get 300 plus the 5 times 80, I get 700. Construct a 68% confidence interval. 700 plus. Yeah, did we sample over 30? Didn't say. Oh, here it's 30. Yeah, we 30 or more. We're good. It's a regular old Z curve. So 68 plus or minus one step of width, bingo, 40. If you want to be 70 or 88% sure you got enough, how much should you stock? Okay. 700 plus, look up the 88th percentile for me. You need to step off 1.18 steps. Okay. Woe is we, woe to the you who do not know how to use the normal distribution. Woe to you. On the average, each dollar of advertising generates how many bags of chips sales? Okay, so here's your equation. If I spend $1, $1,000, I'd have sales of what? 305, right? $2, and I'd have 310. $3, I'd have 315. Every $1 increase in advertising generates 5 bags of sales. Okay, this is the most important number in the formula. It is the slope. The slope is the multiplier, if you will. X gets multiplied by the slope. Repeat how I got there? Okay, so why, your first intuition was be to plug 1 in there and you get 305 and say, oh, 305 is the answer. No. It's 305 if I spend $1 on advertising. It's if I spend $2 on advertising, it's 310. If I spend $3 on advertising, it's 315. $4, it's 320. Every $1 increase up there was met by a $5 increase in the number of bags. The slope is the multiplier. It multiplies, and it is how we can measure advertising effectiveness. It is our means of measuring advertising effectiveness. The 300 is how much demand we would have if we spend no money on advertising. Now that is not insignificant or not important. It represents what? The brand loyal portion of your marketplace. It represents the brand loyal portion of your marketplace. Okay, when I was young, there was a toothpaste called Ipana toothpaste. It was popular among the kids.
What was it?
Ipana. Didn't do crap for your teeth, but and it is bubblegum flavored, I think. But it ran its normal course. I think Procter and Gamble or some other big company had it. They dropped it. Okay, because they just weren't making it. Just wasn't doing well. A young entrepreneur comes along, picks it up for nothing, gets the trademark, and starts selling it. And there's that brand loyal portion of the market. Remember that as a kid. And it's not a slam dunk, but it's a profitable little product that you can still give it for the nostalgic individuals out there. All right, that's it. Oh, our calendar. Shooting for Tuesday for the final exam, 6:30 to 10:30. You should not need 4 hours. I'm going to start spraying you with cold water about 9:45. Get you out of here. Okay. There's no decision trees. It's all cookbook stuff. You got your page 24, your page 30 and 31. Geez. Do a little work ahead of time so you're not sitting here learning it for the first time, and it won't take you any time at all. Gee.
How many questions is the exam?
4 or 5, like the sample. Let me know if you find any typos on that sample, because I did it under duress, and I really didn't have a real good attitude about what I did. You don't do your best work when you got a grudge about it. All right. I am here on Wednesday if you need help with your papers. You want to commiserate about your exam. I'm here on Saturday from 9 to noon to help you with the papers. The papers on the syllabus, I had them do Saturday night. Let's make them do Sunday night, okay? Sunday night, midnight. I got to get the grades in by Tuesday, midnight. That gives me 2 days to do. I got to read about 65 of these boring things in 2 days. 35 or so from here, and I got a grad class that's got a project due to it.
Do we just email it to you? Or
Email it to me, regular email. Don't use Canvas email, please. Okay. We're going to shoot for 6:30. We don't have an actual time in the portal for professors. It gives you your scheduled final exam time. It's blank. So we're shooting for 6:30 on Tuesday, our normal time. We got that other class in here, and I'm not sure if they have a final and when it is. So we may have to play musical classrooms. Hopefully we can find a classroom that's available. We know this one would be available at 8 o'clock, but instead of going from 8 to midnight, I would like to, which is several hours past my bedtime. I don't want to bring my jams in. I don't think you want that either. All right, we're not done. Well, you can take off if you want. I was taking a break, and then I'm going to give the demo of how to do the case study for you. So, all right, any questions before we take our break and go try and wake up? All right, see you in 20 minutes.